So it's interesting, I've been coming to all these workshops, that each one takes what is a large interrelated subject and takes a slice of it. So obviously the whole thing really is a soup, but we look at slices. So I thought, what should I do in this slice? So I thought that there was something I'd done some time ago about dimensional reduction and design and being efficient, which I never really talked about, and which kind of illuminates a bunch of other things. So I thought, okay, that would be an interesting thing, hopefully, to talk about. So this talk is concerned with general principles for Bayesian design of experiments. And the point is, these are general principles, so you may or may not want to do it the way I do it, that's fine. There are many things, but if these are some extra things you can hold in your mind when you're designing, okay? And so we have different levels of accuracy for our simulator, and that's going to be relevant. So the key thing to remember is that Bayesian design is computationally a very expensive thing. Okay? If you think how, in principle, I can say exactly how a Bayesian design should be evaluated. I say, so my design here is choosing which values of the simulator inputs to run to give me my best chance of learning about the whole simulator. Okay? So I think, well, I could make this design. Now, how am I going to evaluate that? I'm going to say, well, I could make certain observations from it. If I made those observations, I would have a Bayesian inference that would be often with an MCMC that would tell me what I now think. And then I would then have to optimize whatever thing that the design was intended to do. And then, but that's just one sample from one evaluation. I'd have to keep sampling from this possible design. For each sample, I have to do the inference and then do whatever it has to do. And I have to do that for each design. Now, computationally, that's potentially a very hard task, which is why you don't see that much Bayesian design, and at some level, everybody has to trick that because it's expensive. It's more expensive than the simulator usually. Okay. So we're concerned with simulators with many inputs and many outputs, all of which we want to learn about. And the top level simulator is expensive. So effectively our method is to use many evaluations of the fast simulator to give us like a sensible prior ideas about the slow simulator, which means that we can do an intelligent small sample design. And we're going to illustrate using an oil reservoir model, just because I've worked on those quite a lot. So a little bit about oil reservoirs, so we have a thing in our heads. So an oil reservoir, as it says here, is an underground region of rock with oil and gas and things in it. Okay? And so a simulator models the flows underground using things like Darcy's laws and various fiddle factors to make them a bit more realistic. So the inputs will be features of the geology, things like permeability, porosity, fault transmissibilities, and aquifer features and stuff. And the outputs are what you see at the well. Okay? So bottom hole pressures, oil production, water cut, water rates, things like that. Okay? So we're going to do a simple example, and it's meant to be just big enough that we can sort of illustrate without drowning in too much detail, but everything we do is designed to scale up. So a reservoir model, like many physical models, is solved on a grid. So this is 48 by 26 by 25. Each cell is a rock with certain properties. Okay, so this is probably an early stage part of the history of the reservoir. There's one injector well and 4 producing wells, and it was given to us by colleagues in the oil industry who say this is an early training example people often use. So the outputs of the model are things like pressures, production rates, cumulative production, and a variety of things. Now, obviously, in principle, we'd like to know about all of the behavior of the function, but just to make it an example that we can do on one page, we're going to just take a particular time point, okay, and at that particular time point, there are 65 outputs. So that's enough for the example. So the inputs are, when we reduce it, are 20 scalars controlling various features of the reservoir. So that is quite a slow simulator, so we want to coarsen it. So we have 25 layers, we coarsen it to 2. You can't coarsen it just to 1 because there is a sort of travelling up and down, but we're going to push the coarsening as much as we can. So that gets us from 35 minutes per run to 30 seconds a run. So we can do a lot more runs, okay? And then we evaluate the course simulator over a big Latin hypercube. Okay? So a couple of points about this. If we were doing it for real, we would not coarsen it quite as much. We're doing it that way because the danger of, if I do an example where the course and the find are very, very similar, you say, well, that's no big deal. They were just like the same simulator. So we wanted to make them very different. And we wouldn't actually do 1,500 points. We could do it with much less, but we didn't want the feature of can we estimate the course simulator to muzz up whether we can design. Okay? So we are now going to talk about how we design generally, and we'll pull it back to the example. So this is a slide I always have, but it's going to be key to what we do here. So I'm going to do a Bayesian design. So in Bayes analysis, we have 2 basic choices here, even though people aren't really aware of them and always choose, in my view, the wrong one. You can do a full Bayes analysis based on fully probabilistically specifying everything, or you can do a Bayes linear analysis based only on taking expectation as a primitive, in which case we specify whichever means variances and covariances we're interested in. See, in full Bayes analysis, you haven't got that luxury. You need all the probabilities before you have any of the expectations. For the Bayes linear analysis, we can be a lot more modest. So probability is the common choice. Everybody here probably, well, almost everybody would use probability. There are advantages in working with expectations. It massively simplifies the uncertainty specification. It massively simplifies the analysis. And actually, the foundations are better. So it's an interesting question, which is the right primitive, and in a different talk I will try and convince you that expectation isn't just handy, but it's also appropriate. So let me put down a couple of equations here. So Bayes theory with probability goes on a single equation, Bayes theorem. We have here the 2 upgrading equations where there's a y vector we want to learn about, a z vector we observe. We adjust the expectation, we adjust the variance, and again, exactly why this is the appropriate thing. There, it's sort of you're projecting into spaces. It is in fact very natural, and you probably use these equations like many times, not really thinking of them as the Bayes linear equations, but they are appropriate and powerful. And the point I want to make here is I am just going to make the point about practicality. I said at the beginning that full Bayes calculations are complicated and expensive, so reducing the complexity gives you a much better chance of actually finding a good design. So if people still want to be probabilistic in their final analysis, that's fine. There are many good reasons for doing that. I suggest you might think about, if you're looking at a design problem and thinking, gee, I don't know how to design for it, it's just too complicated, doing a Bayes linear design, even if you're going to do a probabilistic analysis, is an interesting mixture and would allow you to do a lot more than possibly you can do at the moment. Okay, so we have an expensive function. You know what we're going to do. We're going to emulate it. So here we go. So we have a function. Anyway, my notation, we have a function. Okay, so our simulator takes inputs and gives outputs. So we have an input vector, system properties, like permeabilities, porosities. Output vector, system behavior, what's happening at the wells. If it's expensive to evaluate, for example, an oil reservoir simulator, then we have to treat the function as uncertain, except at the points that we've evaluated. So we want a description of our uncertainty about f of x for each x. We call that an emulator. It's effectively an approximation to the function plus an error of approximation. And we either do a full probabilistic fit for full Bayes, or we just try and get means and variances and covariances, which is much easier if we're doing a Bayes linear fit. So what is the form of the emulator? There are many ways you can emulate. Here's a very common one that we usually use. We write, so f sub I of x is just a particular output, like the oil production at a particular time, at a particular well. Okay, so we write it as a sum of 2 things. You notice I have a notation I like where I put a plus with a circle, just to mean I'm adding them, and by the way, they're uncorrelated. Yep. So we have 2 terms here, and we have the global term, where we have some deterministic functions like polynomials with scalars that we have to work out what they are. And we have the local variation. So we fit a surface and the residual, because the residual is continuous, because the function is continuous, so the mismatch between the surface we fit and the true function is a continuous function. We treat that as a random process, and so the interesting thing we want to know is what's the correlation length. If I know the value of the random process at one point, how far do I have to go before I don't know it at all? Okay. Now, the names global and local are very important here. So I can learn about the global variation by putting points anywhere. I learned about local variation. I have to get up close to the point where I'm interested in u of x. Okay. So what we're going to say here, and I'm probably going to say it on several slides, is that you can't really design for local variation. Any different design that you scatter about will tell you about local variation where you've put the points. Global variation you can learn about because you're putting points in, and anywhere you put the points tells you about them. So in the end, we are going to basically be trying to identify global variation, and that will drive our design. Because two designs will be different because one will tell us more about global variation than the other, and they'll both tell us about the same about local variation, as long as they're fairly well scattered. Anyway, so we want to, we're still looking at achieving something that we can design for. So we're looking at small sample designs. We can't put loads and loads of points on. We're putting a small number of points on. So identifying the key features of the emulator will show us what the key things we need to design for are. So what we have is always an important notion in emulation, and it's super important in design, is to think about the active variables. So for any individual output, every input is relevant. Some inputs are more relevant than others, and the ones that are most relevant we term the active variables. And we often try to find a collection. I mean, if we're lucky, we'll find a small collection. If we're unlucky, we have to be very unlucky not to be able to reduce the dimension quite a lot, and we tend to write our emulator now like this. So our function is a function of all the inputs. We write as a function, a global function of the active variables, because if an inactive variable shouldn't be in there because it hasn't got much of an effect, plus a local variation in that active variables, plus a bit left over because we've ignored everything else, and that what was left over is a nugget term which has a variance, hopefully not too big, but it doesn't have a correlation. And let's just comment on that. This emulator does not interpolate. It doesn't know because it's not paying attention to the details of what x is, so we tend to ignore that altogether and just say that my emulator tells me what's happening with an error on. So when people first see that, they say, well, I like my emulator to interpolate. That's a good property. And they show me a two-dimensional plot, and they say, you know, f of x1 and x2, I like that it goes through all the points. Sure, but when you have a 100-dimensional input, and you can reduce it basically to a 10-dimensional thing, suddenly having a little bit of variance is actually a small price to pay for a huge reduction in a dimension, because it's a dimensionality that is killing us. Okay? So small sample designs for computer experiments. We've divided into local and global. We've said that it's more effective. I mean, the thing about the design, two different designs that will make them different, one tells you more about the global than the other. So therefore we need to put a lot of effort into constructing the global form. So when I always say that, people say, well, okay, fine, but I quite like just making a nice sort of Gaussian process, which is fine if you have a lot of points. The fewer points you have, the more actually thinking globally is important. Okay? So we need to firstly identify the active variables. And secondly, when I say put a lot of effort in, sometimes people say, oh, do you mean fit a very high order polynomial, like you do polynomial chaos and just chop a few off? And that's not what I mean. I think that a good global form is quite simple. Firstly, because you can only design for simple things, and secondly, because a simple global form should reflect the judgments of the expert about the views of these variables. I mean, these things, because it is a function of something, you know. So if you're asking somebody who understands the system, you know, if I up that parameter, if I up the porosity, you know, is that going to increase oil production? Is it going to decrease it? People will have views. Okay? And you're really trying to capture effectively our understanding of how the inputs affect the outputs. That's what the role of the global model is. And I mean, somebody might have a very complicated view, but typically they will actually have quite simple views about basic things like monotonicity, like, oh, there's an interaction here because it depends on this other thing, so that we can build in, but really it's quite simple things that capture key features which we can design for. Now, I'm not expecting all the outputs to be manageable in this way. I'm looking for those outputs that can, because those ones we can design for, and the other ones we can't design for anyway. I mean, we'll have a fairly well scattered thing, so we'll learn about them, but most designs will tell us roughly the same about them. Okay, so we want to identify which outputs to design for. I mean, again, a design that tries to match every single thing will just become kind of bland soup. We want to know the main active variable inputs for these, and the important basis functions. So that basically is the key role of the course simulator. Okay, so the reason we need the course simulator and to do many runs of it basically is to do this job. Okay, because I mean, you need many more runs basically to identify the form of a model than to fit the model if you know which model you're fitting. Okay, and I could point out here that I said that's the key role of the course simulator. What happens if you haven't got a course simulator? Well, you put a human in the loop, and experts will have judgments about this. So experts can act as surrogates for this. I mean, you won't have seen it coming out of the computer experiment, but experts can effectively do versions of what I'm doing now by an understanding of the processes to give you a way of doing these things if you haven't got one. But we're assuming that we do. Okay, and then we may not be able to design for all the outputs as I said, but depending on my time, I want to come back to this. I tend to do what we call history matching, and history matching is a very iterative process, so I maybe can't do this for every output initially, but outputs will have more chances for coming back in. Yeah? So, we have a full simulator and a course simulator. We have many runs of the course, which we want to use to build a small sample design for the fine. Now, if there are lots of outputs, like 65 or 650 or 6,000, a design for all of them is kind of a design for none of them. So we want to effectively identify a good collection of outputs to design for. Okay? So my next principle is that for small sample design, you probably want to look at individual outputs after you've done a bit of data sort of analysis of them and sort of a bit of data reduction, rather than looking at combinations of things. Yeah? Because as I said, your only chance for a small sample design is to have a simple and interpretable global function, and individual outputs do have that because they're driven by certain things. Once you start combining very different quantities, for example in principal components, you've lost the simplicity of the structure, and you've lost your ability, I think, to design for it. Okay? So here, I don't know what people know and what they don't know. We're talking about dimension reduction. So here's something, if you don't use it, just to add to your toolbox, and when designing, and it's an interesting thing to do. So we have many outputs. We want to reduce the dimension reduction by just choosing some of the outputs. Okay? So what does principal variables do? So we've got, here it is in general. We have a set of random quantities, W1 to Wm, and the correlation matrix R. Okay? So what we do is each variable is scored basically by sort of the average of its squared correlations with all the other variables. And the first principal variable is the one that has the most average correlation with everything else. Okay? We take that out, okay, and then we look at the partial correlations. So if you can't remember what partial correlation is, okay, so I have, what's the partial correlation of one vector given another vector? You take this vector, you do a linear fit on the other vector, and you look at the residuals and you look at the correlations for that, and it's given by that formula there, which in fact you'll recognize, where you might, when I started I wrote down an adjusted variance formula, and basically that's it. Again, it's just that comes from usually from a sample variance matrix rather than a prior specification. So you write down that. Okay, so having removed your first principal variable, you repeat the calculation to identify a second, you repeat the calculation to do a third. Okay, so you repeat until sufficient variables are chosen so that the standardized partial variance in each remaining quantity is small. Okay, so the principal variables selected this way will be the most informative subset in the sense that if you know them, you can then partially recreate everything else, and you can better recreate everything else than by any other subset. Okay? So I learned about principal variables from Jonathan Cumming, who I forgot to say at the beginning is my co-author in all of this, because he wrote a very interesting paper on this that I will reference at the end. Okay, and if you're thinking about dimension reduction, it's a useful thing to have in your toolbox. Okay? So in our example, we take many runs of the simulator, we build the correlation matrix, and so that's what we're going to do. Okay, and we design principal variables from that. So what happens when we do it for the reservoir example? So we are going to identify a bunch of outputs. So there is a lot of correlation in the outputs. So in fact, we take the 65 we started with and we boil it down to 15, and each one of them basically accounts for 95% of the variation in everything else. So we have things which hopefully we can design for, which, so that's quite a big reduction. Now, just to show you what it is, so I'll show this picture 3 times. It's only the first column we're interested in here. So these are the things. The prefixes are W is a well, some of the variables for W1, some for W2, W3, some for well 4. The G is the gas injector. The things afterwards are which variable we selected, and they are, okay, so pressures, bottom hole pressures, gas oil ratios and things. Okay? So these are the variables we've selected. Okay? So we're emulating, okay, so now we need to say how we're going to emulate on the course simulator. Okay, so let's just say, let's now jump this and just say that there is a lot of methodology for fitting emulators like this. Okay, so again, my only comment on this is that when people start, they like to fit the emulator in one go, because we're starting to throw it into a likelihood optimization machine or something like that. My strong preference, for reasons that were discussed in the first 2 workshops, is firstly to fit the global form and then take the residuals and fit those, to fit your process to those. I find that works hugely better and is safer, and unless you're really expert, it's a lot more less likely to lead you astray. So you then, as we said, you look at the scientific plausibility of the global forms. Careful diagnostics, obviously, and there is an uncertainty here in the regression coefficients from the course model that often we'll ignore, because compared to the difference between the models, you know, that's small beans. So when we do this, okay, so we're going to do a stepwise search to identify active variables, and in fact we decided to go up between 3 and 6. So we find them by stepwise find me active variables programs. We then take effectively we're going to fit linear, quadratic, cubic and pairwise interactions. We decided, obviously we could have decided something else, and we then do a stepwise delete on that. And so having done that, we just get our residuals, and we do. Jonathan was a fan of variogram methods at the time, so he used that to fit the residual process. Okay? And so the variation of the residuals we treat as just parameters that we've fixed, given that we've estimated them from quite a big sample. So there we are. We see that, in fact, only 8 variables are actually identified as active. Great. The less we have, the easier it is to design. We see here the number of model terms and the kind of R-squares we're getting. Okay, some of them are a bit higher, some of them are a bit lower. We reckon that they're big enough that it's actually worth actually trying to design for them. So we now have to link the course and the fine emulator. So here was our course emulator, where I've now bundled up the residuals into, I've now called it the residual course. So our emulator for the accurate simulator. Okay, so we have an emulator for the course. We want to emulate on the fine, so we need to do something. Okay, so this is the form that we decided. Again, there's a lot of flexibility on this, but we allow ourselves to rescale each one of the regression coefficients individually. We rescale the residuals, and we introduce a new process to soak up everything that's new on the fine simulator. Okay. Obviously, there are many ways you can do this, but we find that's quite a nice flexible way. Now, it's an interesting question that, again, this is what you get from doing a careful job on the global, okay? Because people often take a course and they say, well, let's just add a bit or we'll try and add a bit which is a function of x, but it's sort of in some complicated fashion. Is it really worth getting into the global form and tweaking each coefficient separately, or is it basically just a shift? So because this was just an example, we actually had a big sample on our fine as well, which we didn't use for anything apart from at this point. We said, well, what are the coarse and fine regressions basically multiples of each other? Is it actually worth individually tweaking each one? So we fitted them, and yeah, I mean, the terms in the regressions were important on both, but the coefficients were very differentially changed, which you would not be surprised about. These represent processes that are happening, and basically the rate at which things happen, everything changes, you know, at some level. So the flexibility of changing each coefficient is important, and that's again an argument for having a global which allows you making that explicit. Okay. If you don't put the global form in, you lack the ability to do that. Okay. So we have to structure our beliefs for simulated differences. So we need a mean and variance matrix for the scaling parameters, and mean and covariance for the residual process. So problem specific, obviously, but a natural thing to do, well, it depends on your human in the loop, what their view is, okay? But you might want to set each mean to 1 so that you know, you're varying around the prior value. You might, for example, set all the variances and correlations to be the same, just to simplify the number of parameters. You might be much more careful about this. Okay. Now, if you do it the way I just put up there, all of the variances are the same, all the correlations are the same, then it's interesting that if I think about evaluating a function on the coarse and the fine and looking at the difference, there's actually a simple linear model for it. Now, that only comes out by doing the calculations. But so there's something I said here that once you've actually specified these means, variances, and covariances, I've now specified all of my uncertainties about f of x, and I've specified my covariance between f of x and f course of x. So Bayes linear things will now happen, and I'm just making an observation here that there is nice linear structure in here if we choose to use it. So we now get to our design objectives. We select a small, so the idea is we select a small tuning design effectively to work out what we think about those things and check that we're about on track, and then we do a fitting design using our tuning parameters. So I'm conscious that I'm running out of time here, so, or I will be because there's other stuff I want to say. So so what we want to do is, so what is our design criterion? Our design criterion usually is to reduce variance. Well, there are many criteria we could have, but let's say it is. Okay. So again, a typical Bayes linear calculation is to look at the resolution, which is, so the last part of that is the amount of variance we took away, and then we scale it by the original variance there. That's something that's called the resolution of an adjustment. It's a straightforward thing to compute. The nearer to 1 it is, the more we've taken all the variance out. The nearer to 0 it is, the more variance that's left. So what we do basically is we use our design to learn about the tuning parameters. We choose a design, and how we do that I'm going to talk about very quickly. Okay, yeah, okay. And so we have a second one. Okay, so our second stage is we now have tuning parameters which we've worked out. We plug them in, and we do a second stage where we want to choose a design that reduces our uncertainty about the function over the whole space. Okay, and let's not talk about that very much because I want to talk about how we do that. So the basic thing is you have a design criterion. So how do you then effectively find designs which maximize that criterion in high-dimensional spaces? So now I want to talk about efficient designs for any criterion that you might use. Okay, so we learn about many outputs from our experimental design. So if a particular output is mainly driven by a particular set of active inputs, then we would like our design to be informative in that subspace. Okay, so the active inputs will be different for different outputs, but there will be interlocking, and that's what is a typical feature. So let me quickly do a quick concept example to make it clear. So we have two outputs. The first output has active inputs x3 and x4. The second one has active inputs x5 and x6. Even though we have 4 inputs, it's clear we only have 2 separate, independent, 2-dimensional problems. Okay, so we should not think of that as a four-dimensional problem. We should think of that as two-dimensional problems. Of course, that was great. It's usually not that simple. So what we usually have is effectively active inputs popping up all over the place. Okay, so now suppose we have that. Okay, so that it's not so simple. So we have two four-dimensional linked designs, but we now notice that if I told you x1 and x2, then the functions would be independent, because there's no more any crossover. So once I've fixed x1 and x2, I can reduce it to two independent two-dimensional designs again. Okay, so we have the notion of border block designs. Okay, so if in that case, what we would say is that x1 and x2 are the border, x3, x4, and x5, x6 are the blocks. And what we mean by a block, so in that structuring, is that blocks can only interact with inputs in one block can only interact with inputs in that block, and the border inputs in the border can kind of interact all over the place. Okay, there are standard algorithms for identifying borders and blocks. They take the adjacency matrix of the thing and rearrange it until they've found one. So let's now quickly say how it simplifies our design thing. So there we are. We have two things, two different criteria based on the same design. We only have one design, and it's going to be evaluated on both outputs. So now let's suppose that this was the case. What we would do is that we would generate a lot of candidate designs. Okay, firstly we would start with, say, a Latin hypercube on the border. We would then generate a lot of hypercubes on each block separately, and choose the hypercubes which optimized, gave us best values of our criterion. Having fixed the blocks, we would then take the samples on the border and choose the hypercube which then optimized our design. Having refitted our border, we would then go back to the blocks. So we have an iterative procedure. Okay? So what it is rather than having one high-dimensional design, we have an iterative approach on low-dimensional designs, which is much, much easier to deal with. Okay? So again, it depends heavily on the speed of the Bayes linear calculations to make this tractable. So let me quickly go through. So in the example, okay, we make judgments about the quantities. We just to make the example work, we have a border block set up like that. So what we therefore do is that we have a three-dimensional border, and we have our three blocks. So we exactly run that algorithm. It doesn't take very long. Okay, and we get our tuning design. We in fact chose a design of size 6 observations just to allow us to do this. And here's the design. Let me not talk about it. It's reasonably scattered, I guess. Okay. And everything else just goes into a sort of generic Latin hypercube, because most Latin hypercubes will be similarly effective in the design. And there's a final column on this which says that when we do our diagnostics, we think, well, 7 of them, the ones we've starred, look really good. The other ones possibly we have problems with, which suggests that maybe we've over-coarsened. So we're in fact just going to design for those 7. Okay, and this gives us a simpler border block design. We use that, and here's us. In fact, it's still a problem. You're still trying to search high-dimensional space. I think we think, so the question is, how many points do we evaluate, and how do we search? So we chose to do it by a stepwise add, like 2 points at a time. And you can see our adjusted variances, and this is the kind of picture we would look at. We haven't actually done the design. We're choosing a design here. We say, if we had the 6-point original tuning design, it would reduce that much variance. Our optimum for adding 2 would reduce the variance by more, and effectively we look at curves like that to see the trade-off between increasing sample size and how much variation we get, we reduce, and at some point from there we stop. You can see it's sort of leveling out at the top there. So there is a statement here, okay, about, okay, so I told you very quickly the fact that there are methods that you can use and that you can structure them, and that there are criteria you can pick, and they're Bayes linear criteria, so they're computable. Okay. When you've done that, of course, one of the reasons we want to be efficient in this design is because when we've got it, we hook up to our fine simulator. When we've done our design, we want to do all our diagnostics, and we want to pursue that further. Okay. So there will be, the small sample design will eventually be augmented, but how it is kind of we wait to see we've done the tuning and the fitting design, and then we see what that suggests, and we might send that back down to the course model for further investigation. Oh, okay, so yeah. So one of the reasons I was hurrying was because we had very interesting talks yesterday. So I thought, let me just make a couple of comments on two of the talks yesterday. It was a very interesting talk that told you a bit about history matching. So history matching, so why am I not bothered about designing for all the outputs? Because I am going to do history matching. Okay, so history matching is the process of determining the class of input sets for which the history, if I run the simulator at history, I'm not too far away from what I observed in the real world. Okay, so we have some historical data. So in the oil reservoir, we would have data on all of these things. Yep. So history matching is choosing a geology such that when you run the simulator, the output is not that different from the real world. Okay, and not too large is by the number of standard deviations. Okay, so history matching is an iterative process. You emulate some outputs. And effectively, we've talked a bit about that when I talked about which one. They have to pass a bunch of tests, and we've now emulated them, and we now think they're good enough, effectively, for history matching. In each wave, we will resample and we will repeat this process. It's not a one-time deal. And there's another point I wanted to make, was that there was a question that came up, was how do you get smaller and smaller spaces, how do you get points in the non-implausible space? And so I told you about border block designs, that border block methods are, again, exactly the same way that you search for points. You appear to be searching a very high dimensional space, but as I've tried to convey, you're actually searching structured lower dimensional spaces, and that turns what is a very high dimensional space search with small areas of probability into structured lower dimensional spaces which are much easier to search. So think about borders and blocks. Think about the fact that a function, it may be better to emulate the function than, even if the function is fast, that you're trying to match, because it gives you structure, it gives you border block structure. And my final comment, so Liana gave a very nice description of verification, and so something you will notice from what I did, I have this slide and then a concluding slide and then I'm done, okay, is that I put up a coarse emulator, and then I said, well, there's a fine emulator, and it's not the same as it, because what I've done is I've rescaled. Okay? So now this is a problem that we did quite a long time ago. If we came back now, we would be not running on that size grid. We would have a much finer grid. Yeah? Okay? So this thing that we call the full simulator is itself a coarser simulator for a finer model. If I could run the finer model, I would. If I think about model discrepancy, I would want to get a much finer model before I started linking that to the world. Okay? So now, of course, I don't know what that is. At that time, I hadn't built it. But just as I had beliefs that go from my coarse to my full, I can emulate my coarse to the my current to the emulator I would get if I much refined my grid, effectively by doing the same thing again. All I've done is that I've now rescaled my parameters, I've rescaled my residuals, and added a new term. So I can't do I can't run the higher level model, but I can emulate it, okay? And that model is much, so if I think about my beliefs about the real world, my beliefs about the real world are much better described by saying I have beliefs about the better simulator and then how that relates to the world, okay? Everything I do in the Bayes linear world, if I had, is just going to take an emulator, so it could take that emulator at the bottom just as easily as the one at the top. Okay, so all my calculations will be exactly the same, and it has the huge virtue of just being a better description of my uncertainty about the world. So this is what verification is, to treat an abstract concept as if it was real. I have my little simulator here. What do I mean by saying it tells me something about the real world? It tells me something about a much sort of better version of the simulator, which in principle I can imagine and one day I might build, that will then link me to the world. Okay, so that's verification, and effectively it was examples like this where I was very conscious that the model that I was building was only an approximation to a much better model, and that I had a very clean way of linking them all up that led me to thinking, well, this is what we should always do. So I strongly recommend you add that again to your toolbox. So concluding comments, we've presented very briskly a pragmatic approach to experimental design. Hopefully there are things you can take out of that and put into your workflow. It's the speed of the calculations in the Bayes linear world that makes us able to do all of these things. And fast approximations and dimensional reduction. Yep. Notice, so my final comments here are our ability to do this relies on our ability to, on the availability of fast approximations. So it is good practice when anyone builds a simulator to think, oh, if it's a really slow simulator, somebody's going to have to use this to make sense of the world. We need to give them, to make it easy and transparent to create these fast approximations. So we often talk about, what are the key subjects that these workshops and uncertainty should be about, and good simulator design precedes good uncertainty analysis, and that's just an example of that. Finally, some references. So I stuck at the top, okay, I'm bad at quoting history, but this one, there are a lot of good historical things about thinking about big objects, and the one at the top is a good place to read because there's lots of ideas in there. This is us doing, the Durham crew doing history matching for oil reservoirs. The one that goes into detail into the stuff that I've talked about now is the one small sample design. If you're interested in principal variables, to add them to your box, there's a paper. The reification ideas, there's a paper describing that. And if you, the Bayes linear book is at the bottom. Thank you very much.
Are there any questions? Yeah.
Thank you so much. So I have a question about the choice of active variables using the coarse version of the simulator. This is very attractive. But do you think it's robust enough, or do you iterate?
Well, you notice that we put in a whole bunch of variables to start off doing this, and some of them fell by the wayside at stage 2. So yes, the point about, if you think about small sample designs, yeah, you have to make judgments and then push them and then test them. If I remove that, okay, I could design for everything, but that's really designing for nothing. Yeah. So this is where I talk about interpretability. This is where you have the expert needs to look to effectively to validate this and say, yes, there doesn't seem to be anything super crucial you've left out. Yeah, these ones are effectively following, the kind of shapes, that don't seem crazy to me. So it is quite an interaction between that. Yeah.
With the applied mathematics community, by the way, the multi-level Monte Carlo approach has this same idea of copying. So do you benefit from the same features of less work when you look at differences between coarse and resolution modeling?
Obviously, I did it for 2 levels, but obviously you can do it for many. And in fact, as I said, really I would do 2, 5, and 25 on that. But you'll notice that the interesting question is how you construct those differences. Yeah. So I do not just put in a difference. When you tune each the global parameters separately, you have a much more nuanced difference between them. Yeah, it's not just saying that, there is a difference depending on x. There is now a difference, because I've changed my beta coefficients, I have differences and I have a correlation in distance that comes out of effectively my understanding of the difference in the processes between these things. But obviously everything's linked. Yeah.
Just a quick one. On the block border design, I wasn't quite sure what you were doing with the inputs that didn't show up.
Sorry, can you speak a bit louder?
Sorry, on the block border design, I wasn't quite sure what you were doing with the inactive inputs.
The inactive inputs okay, so the point about the inactive variables, okay, is that effectively, obviously there is a further bunch of effects, but there isn't that much structure to them. So in terms, the view we take is that most sort of different designs will have roughly the same amount of information. So we just do like a maximum in Latin hypercube in them or something like that. Obviously we need to design for them, but but most designs are not that different in the amount of information a priori you expect. One of them might turn out to be great, but right now you have no way of telling them apart. So we just create, so we can just tag on to that, just a maximum sort of design in those, yeah.
Okay, so thank you very much.